Hello and welcome to In Control, the first podcast on control theory. Here we discuss the science of feedback, decision-making, artificial intelligence, and much more. I'm your host, Alberto Padoan, live from a recording studio in Zurich. Quick thanks to our sponsors, the National Centre of Competence in Research of Dependable Ubiquitous Automation, the International Federation of Automatic Control, and the IEEE Control Systems Society. Our guest today is Karl Johansson. He's a professor in the School of Electrical Engineering and Computer Science at KTH, the Royal Institute of Technology in Stockholm, Sweden, and the Director of Digital Futures. Welcome to the show, Karl.
Thank you. Thank you very much, Alberto. It's really a great pleasure to be here. Thanks for the invitation. I'm looking forward to our discussions.
So, first of all, in preparing this episode, I realized that despite the large wealth of Swedish control theorists and the heritage that Sweden has built on the subject, you're the first Swedish person to appear on the podcast. I'm very happy to have you here. Perhaps maybe we can actually start the podcast and kick off things about this specific subject. So maybe trying to understand why is Sweden so strong in control theory, and what was your trajectory? How did you happen to stumble on control theory yourself?
Yeah, thank you for that. It's actually something that I also have been reflecting a little bit now and then. And if you want, I can tell a little bit my story, how I came into the field, because I think the person who is responsible for that is also to a large extent responsible for why Sweden has been so successful in the field. So when I was an undergrad student at Lund University in southern Sweden, I studied electrical engineering, but I didn't study control. I was more interested in mathematics, and I was interested in information theory, communication, coding, and this stuff. I was doing a little bit of teaching. I was TAing in mathematics and physics. And after a couple of years, I started to think about maybe I should do a PhD. And then my physics teacher, I was asking him, what do you think about a PhD in math or in physics? And he had a very strong opinion, this professor. He said, no. If you should do a PhD and you're interested in mathematics and you're at Lund University, you should do it in control.
Okay.
And if we continue a little bit from there, so as I said, I didn't study control. Professor Karl was a very famous figure. He's very famous in the control field, but in Lund he was also one of the big professors. I never met him before. I didn't take any course by him. But I decided to follow the teacher I had in physics. So I'm that old, so at the time you had to ask the secretary of the professor for an appointment. So I contacted Åström's secretary, Eva Schilt at the time, to set up a meeting. And then I got a time for a meeting. So it was a setting where the secretary actually had her office outside the office of the professor, right? So you sit in the secretary's office and you are very nervous as an undergrad student of meeting this giant. Yeah. And when I was sitting there waiting for my hour, so to say, she said, unfortunately now, Professor Åström, you have a very important phone call from MIT coming in. So I think you will maybe have a very short meeting, but anyhow. And then she let me into the office. I met Professor Åström, or Karl Johan, as we say in Sweden. And he asked me to sit down, and we start to discuss right away some exciting research topics. And he spoke and about this, and I tried to follow him on his blackboard and so on. And then after a couple of minutes, the phone rang. And then he answered the phone. He always spoke very loud, so he said with a very loud voice to the guy on the other side, "Oh, I'm sorry. I'm very sorry, but I'm in the middle of an extremely important meeting right now, so I call you back in an hour." And then he hung up. And at that moment, I realized that this is the guy I should do my PhD with. And this is a subject where I should study.
It's amazing.
So since that day, actually, I have been doing control, and I met with the people in the department and so on. And since then, of course, I come to know Åström very well, and I know also his trajectory and his good sense for good control problems and so on.
This is incredible. Obviously, Karl-Johan Åström is a giant in our field. He's done some amazing work in the adaptive control area, in system identification, event-based control, many other topics, some of which I guess we will discuss also later. As you say, then you start your career, your academic career in Lund. And based on the notes that I prepared for today, you do your PhD between 1992 and 1997 at the University of Lund under the supervision of Åström. The subject is relay feedback and multivariable control. What is that about?
Yeah, so actually the relay feedback come back to that very first meeting I just was mentioning.
Okay.
Because the problem that Åström proposed, so he had done some work together with another professor in Lund, Tore Hägglund, on something called the autotuner. So it was to use relay feedback to generate an oscillation in a control system in order to tune the parameter of the PID controller. So that they already developed, it was patented and implemented by a lot of industry and so on. But he presented the problem of, okay, we actually don't know when there will be an oscillation. Not even for a linear system with relay feedback, when will there be? And when I started, as many students, I think I share this with, you are a little bit naive, right? You think that you get a problem and let's solve it. So I thought, okay, this is a great, sounds like a very, I could understand it without really having any deep background in control. So I started to work on that problem. And much later, I realized how difficult problem and that this problem is maybe not solvable in its general sense, but you have to make certain assumptions and so on. But in my thesis, I worked on that in different aspects, actually, both from a more mathematical viewpoint, understanding phenomena that can appear in this very, very simple system. But then I also got interested in using this type of system. So not only for scalar system or CISO system as the original proposal by Åström Hägglund one, but also for multi-input, multi-output system. I even, during my PhD, start to work a little bit on with industry on that problem. So I had some interns at ABB at the time, and I also was interested in, this was a time where fundamental limitations of systems were quite hot topic in control. I did some work in that space as well to understand when will this method work, when won't it work, and how should you design your control. I did a few contributions there. In the end, when it comes to my thesis, putting all this together, I didn't have a better title than just basically listing what I was doing. So that's the reason why it's, that was the thesis work.
The thesis is actually quite interesting and funny. So it's the first time that I will actually read a passage from it, because I was looking at it yesterday in preparing this episode, and it starts as follows. So it says, a conversation heard at a bar in Newcastle, Australia, between a Swedish graduate student and a local sailor. I'm doing research in control. What kind of control? Automatic control. Automatic control of what? Oh, of everything. It's a general theory. This is really the inception of your thesis, the style. And I found it so original, so funny, because it really captures also the difficulties that so many of us control theorists have when trying to explain what we do to a general audience. How did you come up with this?
Oh, thank you. That's very kind of you. Actually, you're probably one of the few who reads who reads my thesis these days. No, it's also, there is actually, it's a truth that passage in my preface. So it was actually my first conference. So after my first year as a PhD student, I went to the IFAC World Congress in Sydney and had a great time. I was the first big trip. And it was not only, so to say, big because the conference was big and you see some of these big names that you have read papers by and so on, but it was also far away from Sweden. I went afterwards together with some PhD students friend. We went hiking a bit and went around and so on. And then we went up to Newcastle in Australia. And actually that very story that you read happened.
It's a true story.
And I thought it was so great. And I was reminded about it when I was writing up my thesis maybe 4 or 5 years later. And then I thought, maybe for someone who is not into the subject, this is a good illustration because, just as you pointed out, I think many of us try to explain for family, for friends, what is control about. And we realize that it's not always. It's a bit like Åström used to say, this hidden technology, right? I mean, we see control when it breaks down. Then maybe someone in the news talk about that the control system didn't work. But as long as it's working, it's just something that is there. And we sometimes have a little bit of problem to describe to others exactly what it is we are doing.
Indeed. So maybe concerning these Lund years, some of the things that I noted down are certainly, obviously, some of the publications that came out of your journey there. For example, fast switches in relay feedback systems. As we were mentioning before, you worked on the relay feedback problem. Maybe just to clarify also for the audience what a relay actually is, for those who are not initiated to the subject. It's basically a sign function that we interconnect in feedback with another system. That's how we can conceptualize it, right?
Yes, absolutely. So mathematically, it's, so to say, this, in some sense, the simplest type of nonlinear feedback system we can think about is a linear dynamical system in feedback with that sign function. And despite that it's so simple, it can actually show quite complicated phenomena that can appear. What is also very interesting, which I realized a few years into my study when I become more aware about all studies going back 100 years in the eastern part of the world, in western part of the world, that this thing about having relays, right? I mean, that was, happening a lot in the 20s, in the 30s, and so on. There was a lot also mixed between mathematics and engineering, where people try to understand the behavior, and things like describing functions come up, and frequency methods, and you have a lot of very early control thing, which was all about this. When I entered into this area, or basically when I was leaving the area after my PhD and went into hybrid systems, I then realized that this is the simplest hybrid system or hybrid control system you can think about. And then you realize also the richness of something like a hybrid system, because a relay system is just a very, very specific type of system there. So, yeah, you're absolutely right that it's kind of something which we today, maybe when we teach undergrad or grad in control, we don't talk much about relays. But it now and then pops up. And for instance, these days when we talk about neural network and neuroscience and so on, and switches, we get back to this about how to model systems and so on. This pops up, and you see that some of these classical problems are very relevant to look into again.
Absolutely. I'm glad that you also mentioned some of the earlier literature, so the literature in the Russian, let's say, literature. I'm thinking about, I hope I pronounced it correctly, Tsipkin, and also going back even to the Luria problem, so interconnection of a linear system with static nonlinearity of some kind. And as you say, the relay feedback system in particular can generate very rich behaviors, like, for example, limit cycles. And I guess maybe to motivate also to the audience why determining whether there is a limit cycle in a relay feedback system. Well, this was actually used basically replacing the controller, using the relay, replacing the controller, measuring the amplitude and frequency of a possible oscillation, and from that basically tuning the parameters of a controller. So that's why this is actually quite important in practice, and then was also, as you mentioned, patented and used in industry, as I imagine.
Yes, that's absolutely right. There was also something which happened my first year as a PhD student. So I went to a very small meeting in St. Petersburg. At the time, we had something called the Swedish-Russian control meeting. On the Russian side, it was led by Professor Jakubowicz. On the Swedish side, it was Åström, Lennart Ljung, Anders Lindqvist, and others. And this was fantastic for me, because that's when I learned early on all this literature in the Russian. And I even started to try to read some Russian papers and so on. I even collaborated with a Russian control scientist, Andrei Barabanov, for some time, and I learned a lot from that. And later on also Megretsky, who is now at MIT, got into this problem, and many others. So I really enjoyed, so to say, learning both the history of the problem, but also you learn people from this, right?
Yeah.
You learn about other works that relate to that work, which I think has been a great opportunity.
Amazing. I hope actually this will spark some interest on the problem itself for, the new generations of control scientists out there. And as you mentioned people, and also you mentioned hybrid systems, I think we have at least two tangents to take here. So one is actually the interaction with people at Lund. In particular, I see that you did interact a lot with Anders Rantzer, another eminent figure from the Swedish school. And as you mentioned, you also move on into the field of hybrid systems later. I'll let you take it from here, maybe.
Yes. Yeah. I mean, Anders was my co-supervisor. So it was great. After I have been in Lund as a PhD student for 2 or 3 years, Anders came back from his postdoc in Minnesota. Anders did his undergrad in Lund and then his PhD at KTH. And then he came, and one day he was standing outside my office, and I was asking if he was a new PhD student. And then he said, "No, I'm your co-supervisor." And since then, we worked together a lot. And having Åström and Rantzer as a team, I cannot think about a better couple as supervisors. It's been really amazing. And it's thanks to them that, they complement very well also in different aspects. But then after I did my PhD in 97, I had quite a bit of discussion with both of them what to do next. I actually thought for some time that I should go out in industry and do different things and so on. Then it happens that Shankar Sastry came to Lund to be an opponent for a PhD thesis. And I sat down with Sastry and we talked a little bit, and then he basically invited me to Berkeley. And that was another game changer in my career, because actually, I tell my students sometimes who are too eager to write papers and to write too many papers that actually when I graduated, I don't think I had a single journal paper published. Then I came over to Berkeley in this extremely dynamic environment. There were so many great people, not only professors, but postdocs and students and so on. But it was also a lot of energy about now, let's see, hybrid system have just started. Berkeley is the center of it, basically. And there was a lot of things going on. So just the first few months, I think I produced more papers than I did during my PhD. And I met, many of those people that are around in my age today. There was several who were at Berkeley at the time, including at ETH, right? We have Jan Lygeros was there, Pappas was there, Maria Prandini was there, etc., etc. So it was a fantastic, so to say, start on the postdoc, but also for the future career.
It's great that you mentioned that, because this is really the impression that I got in preparing this episode. It must have been a really vibrant environment. All of the people that you're mentioning just now went on to do great things. And generally, at the time, it seemed like the epicenter almost of this new topic of hybrid systems, and lots of very cool research coming out of it.
For me, it was also, you talked about the Swedish school before, so in control. So the Swedish school of control has very much been about this, of working on real, so to say, industrial problems, motivated by industrial problems, but with rigorous methods. With methods based on the fundamentals, understanding, and so on. So this was, so to say, what I was brought up with. Coming to Berkeley in Shankar Sastry's group, first of all, it was a very open environment. I met with the people in the group of Pravin Varaya, Tom Hensinger, Edward Lee, San Giovanni Vincentelli, etc., etc. So we all met, and so that was something which actually meant a lot to me, this understanding about the openness of academia, and that you are inclusive and you actually learn from many different people. It can be an undergrad student, it can be an award-winning professor or so. But this thing about actually being very active in that type of spirit was fantastic. And I really try to use both the, so to say, the Berkeley way of working and the Lund way of working in my daily work here at KTH as role models.
This also goes to say how important is the interaction, and also sometimes also traveling physically or figuratively outside of your comfort zone. I noted down, obviously, lots of other papers coming out of this period that you spent at Berkeley. Perhaps the most cited one is Dynamical Properties of Hybrid Automata in conjunction with John Lygeros, Nicholas Simic. I don't know the name of Jung, but certainly also of Shankar Sastry. Particularly found it interesting. This is a very technical paper. It goes into the weeds of providing necessary and sufficient conditions for existence and uniqueness of solutions of such systems, and then really lays also the foundations of standard methods like Lyapunov's theorems, LaSalle invariance principles for hybrid systems. But maybe actually we should define what is a hybrid system.
Yeah, so this actually, it was something that was quite debated at the time because we started our discussion here about relays, right? So that's, we sometimes call a switch system. And so is a switch system and a hybrid system the same thing? What is the difference to a hybrid automata and so? And coming to Berkeley, this was really in the center of it, in the sense that it was really an effort between computer scientists who were founded in formal methods, model checking, timed automata theory, and so on. And with control people now founded in nonlinear control, differential geometry, dynamical systems, and so on. And in the notion of hybrid automata, it's really the combination of these two things. So you understand a solution, not necessarily as a trajectory that we do in dynamical systems, but also from what the automata actually accept, what type of strings and so on. And vice versa, you try to understand now the automata from a dynamical systems viewpoint. So what we tried in a lot of meetings and discussions, and the paper you cite there was maybe the one in the end where we tried to do it in some sort of a comprehensive way, was trying to formalize this so that it's something that people can build on top of. So you kind of do a little bit like you do in a basic book on dynamical systems or signals and system, where you can use the tools to actually then extend and build other methods on top of that. So this is, so to say, the approach we took at the time. And I should say then also, of course, for us in control, we know, so to say, the hybrid systems from a control viewpoint. But I would say at the time, it was a very strong push also from the computer science viewpoint. A lot of computer scientists got interested in this because their systems, their real-time systems, was not just only a computer. It was not just software running there, but they were thinking about embedded systems, networked embedded systems. So you have the interaction with the physics and sensors and so on. So it became like a melting pot where these communities came together and tried to solve some problems together.
This is amazing because it also explains to me, obviously I have this weird role of looking at people's trajectories in this podcast, and I was trying to understand, why did you get interested in embedded systems? And also you mentioned, for example, the interaction with Praveen Varaya about transportation, which comes later on in your career, but also wireless networks. And all of this seems to explain why. So at Berkeley, you really were exposed to all of these different concepts, and probably you started thinking about, how do I actually use now these tools to deal with those applications from a control theoretic perspective?
Yeah, I think, I bet you have a very good point there. And that's, partly due to how you think about science and engineering sciences. It's also how you build an environment. Because in Europe, at least at the time, we were quite used to this thing about that we have individual department of subjects. We have department of communication, department on control, department on this and that, right? And our students were not so much exposed, at the time at least, to other departments. So they worked on this thing in the classical way. What I found at Berkeley then, which I think was a great success, was this thing that you didn't have these departments, but instead you had some sort of methods. You had some problems in this area. And then people were excited about bridging across and find, so to say, new problems which were in the intersection, perhaps between communication and control. And so you are absolutely right. So while I was there, I got interested in this area that we later on came to call network control system. So from a pure control viewpoint, some people just thought about it, okay, let's add now some networks in the control loop and we can do our usual theory. It's just that we add some models for the communication. While the approach we took, and again, I think it's very much inspired by some of those people that you mentioned, but also many others that were around, was, okay, how can you solve the problem from the communication viewpoint? How can you solve the problem from the control viewpoint? But maybe most intellectually exciting was when you put these two together, how can you do communication which is most suitable for control or vice versa? And then you realize things like many people realized before me, that basically the success of wireless communication is basically feedback control, but on different layers in the OSI stack. And I must say, I didn't think about that so much because I didn't know that much about communication before. But when you look into that, you see also that why do we have to solve a control problem by designing the controller? Why can't we solve the control problem by designing better protocol for communication, better sensors, better actuators, and so on? So you get a little bit more a holistic systems view of the problem of control, which I today think is a very useful approach. And for many of us, this is an obvious one, right? But if we look back like we do in this discussion today, you see that this, at certain time, this changed a little bit the way of thinking about some of these problems.
I fully resonate with what you just mentioned. I absolutely agree. So I think actually in many ways, the research that you've done in those years, actually just to contextualize for our audience, we're now moving towards the early 2000s. You move back to KTH and you start looking at, as you say, at network control systems where also you incorporate wireless elements. And as you say, I think it's the research that you were doing also at that time is very actual also today because it touches on so many aspects that I think are still unsolved. For example, the problem of architecture. So how do the different layers interact with each other and how do they affect actually the performance of the system being designed? In particular, as you say, you were looking at wireless network design for control systems. There's a beautiful survey that you wrote with Park, Ergen, Fischione, and Lu. I'll link obviously this publication in the episode notes. And for me, it was actually very, as you say, intellectually stimulating because it shows the role of different communication protocols in control design, which is something that normally, when we write our state space equations or our transfer functions, we don't actually see. But apparently they do have a major impact on the performance of the system that is being designed.
Yes, I mean, you're absolutely right. And let's reflect on that a little bit. So notice that two of the students there, DiMarco and Park on that paper, who are both professors now, one in Korea, one in Italy, you can guess who is where. They really, their thesis were really focusing on this doing wireless communication, wireless networking for control. I was very happy at the time that Karl Fischione, who is a colleague of me now at KTH, he was a postdoc and he had his PhD from L'Aquila in wireless networking. So he was not a control guy. Okay. So we really worked across and tried to, if you want, you can say we tried to mimic a little bit the Berkeley idea. Actually, Pangum Park's opponent was Pravin Varaya. So we were very much inspired by that. We had one thing, which I must say, which is maybe not completely clear from the papers. But one reason why I like to move to KTH was that wireless networking, not only here at KTH was very strong, but we have Ericsson next door.
Yeah.
And this, I learned a lot from collaborating with Ericsson and learning, so to say, what are the problems there? Not only, so to say, where are the communication problems, but where are the opportunities for control? And this is something that we investigated early in a few papers, and then we have that survey that you listed. But what is very nice these days is we see that actually today, the big communication companies, not only Ericsson, but around the world, very much embrace control. They maybe call it cyber-physical systems, networking for cyber-physical systems. They talk about edge computing and so on. But it is really control where they put in the loop. Ericsson Research have a couple of research groups now on control and robotics in this area. So I think, of course, it takes time, but you see that our area of control is really taking place not only at the traditional control companies, but we see that it comes into the communications of what you mentioned, and of course, maybe a little bit more timely these days, we see it also in machine learning and these areas.
Actually, you're already anticipating some of the questions that I would have had for the end, let's say, of the episode, particularly the interaction with industry. I think your trajectory speaks by itself. You've been very successful at interacting with, at solving, if you want, problems that were of interest to specific industries. In this context, as you mentioned, for Ericsson, and later on, as we will probably talk about in a moment, the problem of platooning for freight transport, particularly trucks, and the collaboration with Scania. How does one make that happen, actually?
Yeah, again, sorry for repeating myself now, but I give the credit to Åström, my advisor. This is what I meant was a little bit the Swedish school, that you actually go out there and you take the industry very seriously and you work with them and you allow this work to take time. It takes your resources and so on, but you build relations. And if you have one or two success stories with them, they will keep on working with you and you will be able to use that. So it's nothing like my invention to do that. I realized quite early that this was an opportunity and also maybe a way, particularly in Sweden, to be able to compete with some of the other countries and some of the other universities. So these things that maybe look like just a single paper or two papers and so, there is a lot of discussions about with different industry, with ABB, with Ericsson, with Scania and others, where you start working and start understanding what is the problem, what could we do together here. And early on, we realized that it's not about coming with tools. It's not saying that, okay, I have this method, where can we apply it? It's not at all. So in many cases, you just start from scratch and you learn something that you have no clue that it was a problem. And later on, you hopefully realize that it's a problem that relates to optimization, decision-making, control, or whatever that actually is relevant. And you can have maybe some master thesis student working on first. Later on, one of them become a PhD student. Even later on, she maybe graduate and start working in that company. Then she become a boss in that company and so on. So these things that in some sense, nowadays can benefit because you have your former students and you have your strong collaboration. When I look back at it now, I see that it's been a very, so to say, investment over 25 years. I didn't think about it 25 years. I just did what was fun and I enjoy it. But you realize it's actually been contributing a lot to particularly the Swedish industry and to new problems coming into our area that we have been able to do good things about. And it's something, I talk with my students and postdocs and so on about this and try to encourage this type of collaboration. But it's really, one have to be patient. It's not about, so to say, just writing a quick paper. It is really understanding and, so to say, investing time and so on in this. And in long term, it may become give back by getting new problems, new results, and so on.
I think this is great student advice. You're anticipating part of what I normally ask to our guests. What I get out of this also for our audience is that patience is the virtue of the strong, as the Latin used to say. So maybe we should keep that in mind a bit more often. Maybe actually from here, there were a couple of curiosities on my end that were related to wireless network control systems. And then maybe we can also move on to the next phase of your career, or if we can call it such, where also event-based control, which is related to this subject, comes out, but also cybersecurity, transportation applications. But perhaps I wanted to pause a little longer on the wireless network control systems just to understand also what are the challenges there. I was reading that, for example, sampling period, message delay, message dropout, energy consumption were all motivating problems that you were looking at in developing the theory behind this line of research. Is that right?
Yes, that's absolutely right. So this is what you mentioned there is, so to say, an abstract, so to say, representation of how we can think about and model this system. But I think also it connects a bit to what you mentioned now on event-based. Because in a sense, traditional control, right, is either continuous time or it's periodically sampled. And when you start looking into how wireless networking works and different protocols for wireless networking, you realize that some assumptions that are made early in the design phase of the wireless protocol has great influence on control. So currently, as you know, we are working a lot on connected and automated vehicles. And there, I mean, the early standards that were made are terrible. They assume things like you should sample periodically, vehicles should communicate with 10 hertz, whatever happens, right? While you don't have to be a control theorist to understand that you should probably actually communicate more often if you have other vehicles around or something seems to be happening. If there is no other vehicles around or there is nothing interesting happening, you should maybe not, right? And in wireless networking, the original protocols and the way you build wireless network is very much built on connectivity. So the devices themselves should be able to connect to the network. So this has given us fantastic things like Wi-Fi and, sensor networks and so on. Ad hoc networks that works very well. But this is, so to say, just focusing on that we should be able to connect automatically and then we have the connectivity and we can share information. If we now are instead creating control loops, there are other type of constraints and other type of purposes of what we want to achieve, right? We would like to stabilize a system or we would like maybe to fulfill a certain objective or so, which is very different from what the objective of the wireless communication protocol is about. So in this case, you see, to then start thinking about how can we modify or how could we influence how wireless protocols are working, I think I wouldn't say that there is a lot of influence so far from control, but I can mention a few that has been quite important for me. So there were work done 20 years ago, partly coming out of Caltech with people like Stephen Lowe and John Doyle and many others who start to think about communication systems, including wireless networks, from a control and optimization viewpoint, which, so to say, revealed a few things of these networks, certain properties, but it also allowed us to think about how can we actually modify the networks, how can we take benefit of these things. And these ideas, I think, is still very useful when we think about something as complex as a big wireless network. So if you think about that, to give you a concrete example where we have been contributing a little bit, is if you look at handover of wireless networks, so we take like your mobile phone. When you move, there is a protocol that keep track on where you are, and the base station you are closest to is basically the one that transfer the information to and fro your phone. So this has been there for ages, this thing. It was an early success of mobile communication to get that to work. A mobile phone, maybe you have one or you have two, but it's not a big system, right? When we started to work on automated vehicle, a connected vehicle, and you mentioned the platooning that we have developed, then you have 2, 3, 4, 5, maybe more vehicles that moves together. So now you want these, if you want 4 or 5 mobiles, if you can view them like that, connected in each vehicle, they are moving from base station to base station as they drive on the highway. Now you want that handover to be synchronized, because otherwise one vehicle will be connected to one base station, another vehicle to another base station. And that can create different type of things. You can lose connectivity between the vehicles and so on. So when we realized that, I think now it's probably 7-8 years ago or so, I thought that, okay, people in communication, I went to some of my colleagues here on mobile communication and say, how does the handover protocol work and how does it handle in these circumstances? And it seems like no one really thought about that because you didn't have control people in the standardization bodies, right? They were thinking about we all will work with single mobiles or so, and there will not be any safety critical situation, while in reality we have that. So that is kind of one illustration of a quite simple system where you see that understanding a little bit of control and networking, you can actually change the operation of the overall system in a better way.
I'm very glad that you're referring to the platooning application. It's something that I wanted to discuss at some point in this discussion. For those who never heard the term before, platooning basically refers to the fact that we have, imagine, one car or more than 2 cars, 3 cars that want to cooperatively drive together, exploiting the fact, for example, that air drag is reduced by being all in one line, and therefore synchronize, for example, through wireless communication in order to make that happen and basically drive cooperatively on a road. This was particularly useful in the context of freight transportation. You actually do have a fantastic paper, in my opinion, with Bart Besselink and actually many others, because I will not mention all the other co-authors, otherwise there are way too many. But this is on the proceedings of the IEEE. Of course, I will provide a link in the description. I find the paper particularly interesting because, again, you touch on not only on the communication aspect, but basically on the layered architecture that actually is really inherent, if you want, in this control problem. So here we're talking about coordinating large-scale number of trucks using vehicle-to-vehicle and vehicle-to-infrastructure communication. And the way you propose to do it is to split up somehow low-level vehicle control from middle-level cooperation all the way to top-level fleet control. But maybe I should actually let you tell the story of how this unfolded.
Yeah, thank you. That was a very nice summary. I can tell a little bit the background because the paper you referred to is somehow presenting the solution. I mean, that is many years of work in that paper, and that's why there were many people involved in our group here on that. So it was 2-3 things coming together, actually. So how to do platooning between a few cars or a few trucks and so. That was around. So that will be done in a few different places. In California, there are big projects on that, but also other, for instance, truck manufacturer, car manufacturer have been doing that. We started to work in this problem together with our close collaborator here, Scania. We also worked with Volvo here on that. Doing the low-level control there, I would say it's not that difficult now, given that you have things together. But when we started to work on that, we actually got a little bit ambitious, if I say, or visionary or whatever, right? We start to think about the big problem, kind of what you described there now, which was a picture that came out in the end. So we were thinking about, can we think about the whole freight transport problem as a big optimization and control problem with different components putting together? So the reason why we did that, I mean, there were things that happened. So at Scania, we already have some, let's call it low-level success. So we had some success stories, and we happened to get an opportunity to meet with both the chairman of the board and the CEO. And we wanted to have something not just talking about what we have been doing, but what could we do if we really think big here? So then we start to think like that. If we could take over the fleet management, if we could do the optimization of the routes, if we could do telling navigation of vehicles, if we could automate the vehicle, if we can platoon with vehicle, and so on. And in the discussion with these business leaders, we did some back-of-the-envelope calculations, saying that, okay, if we would launch this system in Europe, across Europe, or let's take a country in Europe. We took Germany because at the time, Scania had a large stake, or there was this discussion about Volkswagen and so on. And we showed that it's enough if 5% of the vehicle had this technology it could have a major influence on the market. At the time, it happened that Scania's market share in Germany was about 5%. So we kind of demonstrated this, and we gathered some data also about some data collection and so. So we built that case, and they say, it's not so that with these business people that they suddenly gave us tons of money, but I think we were just happy that they didn't say that this was stupid. You should not be thinking that big. But so then we start to work. After that time, we start to develop that architecture. We have different projects, different students and postdoc working basically on different layers of that hierarchy that you mentioned. And then when we have developed that, and when we have been writing that paper, then it just become a perfect timing, because that was a European project that started where all the 6 truck manufacturers in Europe was part of that. And they implemented. So basically the overall goal of that project was to demonstrate something called multi-brand platooning. So not Volvo with Volvo trucks, Daimler with Daimler trucks, Scania with Scania trucks, but could we actually platoon together, and could we actually build some of the component and demonstrate it of our architecture? And this was done, as I said, in a project called Companion, and it worked out pretty well. You don't see tons of platooning vehicles and the whole architecture implemented now because of various reasons, right? Legal reasons, business reasons, and so on. But for our group and the work we did, I think this was a little bit a game changer, because I think we realized that let's look at big problems. Let's look at important problems and try to understand what we can do with our tools and contribute, which could actually change the way people think about a certain area. And in many cases, when we look around, like in the business of freight transport, right, there is a lot of split, you can say, in these layers because of industries. So on the top level, you have the logistic company, you have like FedEx or DHL and so on. And then you have, maybe on top of that, you have the customers, which is maybe IKEA or some others who have it. If you move down, you have the road infrastructure and you have the vehicles and so on. And you realize that actually the way that some technology develops the way it does, it's thanks to that company maybe want to protect their businesses, but also it's for us at university and researchers to think a little bit beyond the boundary that we find because of how the industry and the system is working today. And there I think it's an important lesson learned that we could maybe apply also in other areas.
Fantastic. I guess I'm not sure whether I'm wrong or not, but if I understand correctly, you also implemented and basically had a live demonstration in Sweden, if I'm correct, of these trucks actually platooning on the highways between Stockholm and somewhere else, and also coordinating with infrastructure, as we were discussing, and showing that this is actually possible in reality.
Yes, and more than that, I mean, we were all over Europe, actually. We were going, so there was some platooning going from Sweden down to Spain, and there were different things. Some tests, the most, so to say, aggressive tests or the most difficult tests were done on test tracks. We were in Barcelona doing some tests and so on. But there was a lot of things done also out on real highway. And when you do this test and when there is a planning of those tests, you also realize other things which has to do with technology adoption and so on. So the rules, for instance, the legal rules for how to, if you can do platooning or not, is different in different countries in Europe.
Oh my God.
So in some countries, there is a minimum distance you should keep as a driver between vehicle. In other countries, like in Sweden, for instance, it's up to the individual police to tell if you are driving in a legal way or not. So you realize when we are developing this technology and we are testing it and we get, so to say, approval for doing the test, that there is also other things that needs to be handled, which has to do with policies and so on.
I know that it's always difficult to speculate about the future, but do you have a sense as to when we will actually see this kind of technology deployed worldwide and widely adopted?
Yeah, there is two angles to that question that I would like to see. I very much believe in Steven Schladover, one of the pioneers on autonomous driving, a guy also from been leading the efforts at Berkeley. He says that recently he was in Sweden giving a talk saying that in 75 years or more, we will see a whole autonomous traffic. I very much believe in that. There are some problems there which are so hard. So we are not talking about 5 years from today, there will be completely autonomous vehicles and so on. There is so. At the same time, if you look at some of the stuff we, for instance, have been doing in this business of how to do this platooning and so on, some of that goes into the vehicle and become features of the cruise controller. So you can say that what you do is that you build this into the vehicles, and the vehicle become more and more automated. It's just like a car. The difference with a truck or a bus is that you have a professional driver that is probably a much better driver than you and me are, and you built in new feature there that they can utilize. So you basically automate the system, and for these drivers today, if you compare what they did 30 years ago, it's a much more automated system. They are much more an operator of the vehicle than a driver. So I think this is what we are going to see. We are going to see a gradual shift into something where the role of a driver or an operator is going to change. We are going to see more technology supporting various things, including safety and handling difficult situations and so on. One project, just to give you an example, that we are dealing with right now, we know that it's hard to drive when there is suddenly icy condition or snow like we have in Switzerland and in Sweden, right? These tests that were done early in Nevada or Arizona, it's under beautiful condition, blue skies and so. But of course, if this technology is going to really contribute, we need to handle these situations that we have also in the Northern Hemisphere. So these things, there is a lot of these kind of cases that need to be solved. How do we integrate information about the weather condition, changes in weather condition? And there it's not just about, so to say, getting better weather forecasting. It's also that you now have information from other vehicles. You have basically sensors all over the road infrastructure that you can integrate, and you can build forecast based on this information. You see that the whole transport system on our roads is changing, even if the individual vehicles are not becoming fully automated. Mm-hmm. So that is maybe a trajectory I see that we are going to, so to say, work through over the coming decades.
Yeah, so change is always more gradual than we sometimes wish it were. I'm really excited about what you said before about the big societal challenges. It's something that I really want to touch on, but I feel that we're also doing some injustice to some of the other work that you've done in these years, let's say between 2010 and 2020, particularly event-based control and also cybersecure control. I'm personally very curious about event-based control itself. It's a subject that seems to be very exotic, but at the same time seems to also gain some traction again in these years, also with these spiking systems that we've been seeing. What is event-based control?
The very simple principle was this, that, okay, why should we fix it if it's not broken? So let's do control only when we need to. And this, I mean, in the basic feedback control loop, we can think about that from two angles. We can think about it from a sensor view. Okay, let's sense when something has happened in the plant. If nothing happened, we don't have to send. Mm-hmm. Vice versa, okay, let's act if something has happened in the plant. If we have sensed that something has happened, let's then act. Mm-hmm. And then you can combine this and you can make this more and more complicated and so on. So this is a basic problem, basically, of how can we decide when to sense, when to act. How can we design, so to say, algorithm for doing that together with algorithm for doing the control? Mm-hmm. And you're absolutely right that over the last 10, 15 years or so, there have been a lot of work, different aspects of that problem. The early work was very much motivated on what we talked about earlier, on the communicating cost resources. Okay, let's minimize the wireless communication and let's think about it from a sensor network viewpoint. We have limited battery capacities. I'm also very much excited about what you mentioned with inspiration from brain science and neural networks, where, for instance, the work by Rudolf Sepulchre and his collaborator, where you can now think about some of these event-based schemes, so to say, modeling some representation of communication that happens in our brain or in some smaller neural network. But there is also other things. You have the great work in Zurich, right, on the event-based camera by Scaramuzzo and collaborators, where you think about a sensor, an important sensor as a camera, that, okay, let's rethink that and let's think of that from an event-based perspective and how we can now integrate that in various control systems like in drones. So I agree with you that for us in control, just start thinking about control not as a continuous process that is there and is acting all the time and sensing all the time, but actually see that as part of the problem seems to be very beneficial. In some cases, we see it in nature and we can be inspired by nature in that sense. In other cases, we can see it from a research viewpoint, like with the event camera, but we can also see it if we come back to the connected and automated vehicle. If we say now that every vehicle in a traffic intersection can connect with anyone else, you get an extremely complicated network of vehicles, maybe 100 vehicles connected, and it would be very difficult to manage. If one think about it from an event-based viewpoint, you should think about it, okay, which other vehicle am I, so to say, more beneficial from being connected to? Because I can use information from them and then actually make the right decision. So this is for the concept that you sometimes use, and we have projects on that, we call it situation awareness. So we have some specific scenarios we look into now, that you drive an automated vehicle at a road intersection with pedestrian and so on. And you see that you can use sensors from other vehicles because they maybe see what's behind a house or what's behind a big vehicle. And then you use that when you make decision if you can pass that house or that vehicle or not, or if you should slow down. So you see in all these cases, the thinking about events as something which triggers me to actually do something and take an action or not is, I think, something which should basically be in our basic control courses, because it's such a fundamental concept to think about.
And yet it seemed to be at some point a niche topic. But again, you have a wonderful paper called An Introduction to Event-Triggered and Self-Triggered Control, written with Maurice Emels and Paolo Taboada, I believe in a tutorial for CDC. Also, there will be a link in the description. Other related publication, obviously, is one of your most cited, is Distributed Event Trigger Control for Multi-Agent Systems, written with Dimos Di Maragonas and Emilio Frazzoli. Also, delightful paper, very short, I believe maybe 6 or 8 pages at most, but also very elegant. It describes the difference between self-triggered control and event-triggered, so the distinction between how should I actually decide when to act. It's a beautiful area of control, which is also related to some earlier work also by Roger Brockett, Minimum Attention Control, another paper that I invite the audience to read because it's fantastic. And same circle of ideas. So acting only when it's really needed in order to control the plant. And I've seen that actually many of the ideas that we are discussing now have been used also in many of your application papers on wireless networks, and then obviously for connected autonomous vehicles in order to implement also the platooning that we discussed before. I wonder whether this is a good time also to move on to cybersecure control, yet another subject that is incredibly interesting and relevant, at least. I had a conversation, I believe 1 or 2 years ago, with Henrik Sandberg, who was actually my PhD opponent, about secure control. And I was not aware of the so many bugs that actually are targeted towards control systems. And there is a whole literature there, but maybe I should let you also introduce what is the problem here.
Yeah, thank you. I mean, the area of fault detection and isolation in control system has been there for a very long time. And for any big industrial control system, you need to be able to detect if a sensor breaks down or something else happened. It's quite different when we look at cyber-secure control system, because in cyber-secure system, we don't say that nature now randomly break something. We say that, okay, there is someone from the outside who maybe wants the system to not behave well. So such a formulation in control is classical, right? That's the game formulation of robust control. We say that nature now try to disturb the system as much as possible, your controller to try to mitigate that disturbance and make the system under these circumstances be as good as possible. When we started working in this area of cyber-secure control system was very early. I think we had our first paper already 2010. It was connected to that we organized Cyber Physical Systems Week in Stockholm. And we organized also a particular workshop of that week on cyber-secure control. And we had people from a few sites around in the world who already at that point started to work on this. So we have people from some institutes in the United States, for instance, who work on secure of control system like NIST and others. But we also invited people who are more working on security from computer science. And then we have some of the people from our community. And that was a very fascinating discussion because you saw that these people basically were speaking 3-4 different languages. The control people maybe had the view, of course, that the important objective is the control of the system and the performance of the system, right? The computer science, some of these working on security didn't understand what is control. They didn't see what is a problem because we just encrypt all the data and there will not be a problem. They didn't really grasp the thing about the physical part, that you cannot do coding really in physics. The physics is one part, and then there is an interface to the computer system. And then at the time you had the one working more in practice. These industrial people or people at the industry who was exposed to that and just show this plot of how many more attacks there were and how more sophisticated they were, and just saw the importance of actually addressing this problem. So what we did early in our work is a little bit similar to other things I mentioned here. We were looking for some good application, which seems to be a critical one, and that we could learn from in order to see what could we develop, what type of tools for cyber secure control could we be doing. So at the time we got the project actually together with ETH, both the control group at ETH, but also the power systems group at ETH. So we were working together with some company and so on, and we were studying some estimation problem in the transmission grid. So quite specific type of control and estimation problem. And we were showing basically some of the vulnerabilities that are there, but also how one can analyze that and what we can do about it. And then, of course, there have been much, much more work since there. And today I see that some of this is a nice theory one can utilize, and some of this is probably used in industry. We learned also something which was new to me at the time, is that if you work on things which has to do with security, you have to think about security. What I mean by that is that now it's not obvious that the company who are exposed to this vulnerability would like to work with an academic group on this problem. And this thing is a little, nowadays, of course, with the geopolitical situation we have and all the attacks continuously that our industry, our societies are exposed to, it's fairly clear to anyone, right, that this is happening continuously. But it's something which kind of came, unfortunately, that it was a growing attention here of how to deal with this problem. Our approach to this has always been open science, that if we are open with this and we build systems which are resilient now to this attack using open technology, right, we are able to build better systems that can sustain attack, and there will be fewer of these type of vulnerabilities that there is maybe in systems when we don't really know how the systems are acting and so on.
Oh, certainly, open science is something that is important, and I'm happy that you also mentioned its relevance, particularly in these turbulent political times. I guess in terms of publications that listeners can actually go and look up if they're interested in this subject, they can check Cybersecurity Analysis of State Estimators in Electric Power Systems that you've written with Alexandre Teixeira, also Amin Sandberg, and Shankar Sastry. This is a CDC paper that then, I believe, follow-up is also a secure control framework for resource-limited adversaries, published on Automatica in 2013. And maybe actually this is a good time to talk about these big societal challenges that we mentioned before. Obviously, security is one of them. We were talking about transportation and its role. For example, we didn't mention it, but it occupies quite a large chunk of emissions in terms of, let's say, its impact on climate change. And I think there are many others that obviously control has to think about if we actually are to make an impact in the real world. I'm very happy that I have a chance to talk to you today because you're one of the editors of this, or the authors, I don't know how to refer to this, but of this large document that the Control Systems Society has produced. It's called Control for Societal Scale Challenges 2030, co-edited or co-authored with Anu Anaswamy and George Papas. There will be obviously a link in the description. For any student out there or anybody interested in starting in the field of control, it's an absolute must because it outlines so many of the big motivating challenges that humanity and therefore also control is facing. I'm curious about what motivated you and Anu and George to launch this initiative.
Yeah, it was actually a meeting that we had at the CDC where we start to talk about, in the past there had been other roadmaps in our community. There was one led by Richard Murray, for instance. Anu and Tariq Sama had been working on in the past and so. But it was a few years ago that they happened. And a lot of things has happened, right? We have the machine learning, we have the data science, the cloud compute, and a lot of things have happened since then. So we actually talked a little bit and said, okay, it seems to be a good timing. If we should do it, it should really be a community effort. And that I like that you stressed that we were the editor. So we were maybe those who just make sure that our community came together. So what we did was that we organized, first we had a virtual workshop. There were people invited to lead certain area discussions, there were panels and so on. Our whole community were invited to contribute to this. We did that in a true pandemic sense. We did it online, we couldn't meet physically, but it was such a great response. I must say that I think all three of us were quite happily surprised how eager our community were to actually define in 10 years, what should we now work on? What should be the contributions from the control field to these great challenges? And then after that, we decided that we need to meet physically. So we had a meeting actually in Stockholm where we were about 50 people here, sitting for a couple of days, working quite intensively, shaping this. We had, so to say, the starting point already, but now shaping it both into this report, but also into some other material that came out. So there have been like articles coming out of this and other things. And as you have seen from the structure of this document, it's both the challenges, but for the student, I think it's also nice to see, okay, so what are the technology trends that can contribute to the control? And then one go into a little bit detail onto the methodological development where there are some speculations and so. But it also end up with talking about other issues like education. How should we change the curriculum in the future to fit now what has happened around? But also, how should we think about areas like ethics and diversity and so on in our field? So it's kind of try to take a quite big view on our area and try to say, okay, these are thoughts that are around by some of the people in our community. And please look at it, read it, comment it, and maybe use it if you think that is useful to motivate you or your student, and so getting into our field and make a change.
I found it particularly interesting, like the document, I keep going back to it. I've read it probably, well, not all in one go because it's a huge document. It's probably more than 200 pages. But I find myself going back to it more and more often lately because not only it offers the big, really big societal challenges that humanity is facing, including, for example, climate change, decarbonization, but also electrification due to the constantly integrated renewable energy that keeps on being added to the grid, healthcare, sustainable transportation, and also the different perspective that you can clearly see from different voices in our community. I think it really was a nice snapshot at the time. I'm curious whether you think something has changed. So now we're 3 years away from that document. Is there anything that has changed?
Yes, that's the thing. Actually, if I reflect on that, when we started, we had a bit of discussion with Richard Murray, who edited an earlier kind of similar text. And he pointed out that in their text, they have no clue about that AI would be coming back and that we have all this machine learning and the cloud and so on. And I think already in the text you see that we were involved in editing, right? Just the large language models, foundation models, transformers, and this change. I mean, we were not aware that that is going to take off, and we see a lot of things happening in the control. Of course, we have learning for control, and there is some discussion about these topics in a couple of chapters there in the document. But I think the scale of the transformation we see happening now is not really in there. Mm-hmm. Another thing which is not in there either is the geopolitical situation and the influence that might have and already actually have on the research community, mm-hmm. which is another thing that, of course, we didn't foresee, but we see that it has an impact. And I think as a community, we need to be aware and we need to help each other in this type of situation that we are.
Well, this is more of a curiosity of mine, but I've seen one of the challenges that obviously you list in there is sustainable transportation and urban systems. This is something that obviously you've been working on actively, as we discussed earlier. I just wanted to connect this to the Bode lecture. At the time of recording today, we're not in December yet, but at CDC 2024, you will be awarded one of the most prestigious awards in control, as I mentioned, the Bode lecture, titled Semper in Motu, which in Latin means always in motion. I'm curious whether we can have a sneak peek about what you're going to discuss in that lecture.
Absolutely. As you can imagine, I'm intensively working on what I'm going to say. So I could even show you a few slides if you want. The message I want to give is really about how control is in the middle of that transformation. The transformation of the transport or the mobility area. And I really plan to give my lecture targeting the PhD students in the audience and talk about the great opportunity. It used to be so that the automotive area is big in control, right? We did engine control, we did various stability problems of chassis and so on. Now we are in the situation where we go through this digital transformation of the whole transport system, and it opens up to many, many more control problems. And there is around the world many research groups in control which actually do amazing job, not only on developing new methods and so on, but actually implementing things. Either implement them by themselves, and they have labs and they go out in cities demonstrating that, but also in collaboration with various industries, not just the automotive industry, but also other type of industries. So I will try by a few examples, things that we have been doing, actually not going back to what you talk about, but a little bit more things we are working on right now, where we are using machine learning techniques to model automatically traffic and use that for doing control of traffic and so on. So much more in what you said, in a city type of context or in a regional context, where I think we have some exciting new problems that needs to be addressed, but also great opportunities for research for many years to come. So that's the plan so if anyone in the audience don't like this topic, they should not then come to my lecture there. So, yeah.
I'm sure they will, otherwise they would probably miss out. I will probably abstain actually from commenting at length about what you just mentioned. So the subject, as I have skin in the game myself about transport, and I find it a particularly fascinating subject and something that where we could actually, as control theorists, contribute to a lot. But since you were mentioning maybe the digital transformation, I feel obliged to pay justice to also your alter ego. So as the director of the Digital Futures, this is a research center obviously based in Stockholm, Sweden. I wanted to ask you, what is that? How did that come to happen? And basically, what is the vision behind this research center?
Yeah, I mean, the vision is to develop science for the digital transformation of society, which seems to be a very bold thing, but it's a few things that came together at the same time. So if we start with people, we have both our great students, but also faculty and collaborator, both in the city and region of Stockholm, as well as in industries here, that really would like to see much more collaboration around, we can call it a smart city if you want, or you can use some other term, but the digitalization of society. I mean, the digitalization of society is not just buying more computers or so, and it's not just about developing more research in academia. So it's very much implementing, testing, learning from experimenting, and so on. So we came together and were thinking about that, of how to develop Stockholm into a test bed, a digital site for demonstrating some of these technologies. I mean, we talk about transportation here. You mentioned health, you mentioned energy network. We have also water infrastructure. We have the food delivery. We have all kind of, so there are many things in the city, right, that is happening, which is basically flow of information, of energy, resources, and so on, that is being controlled. So how to do that in a more efficient way, in a more climate neutral way, are on top of our mind, but also on top of the mind of the city here and the industry. In addition to that, in research, we need money. And we were just lucky that the Swedish government were thinking along the same line. So they wanted us to create something that could contribute to the digital transformation here. And then we basically decided to do it here at KTH, and we had great support from our leadership, from the leadership of Stockholm University and a few other sites. So this is what happened in 2019, that these things came together at the same time. And then we launched it 2020 in the middle of the pandemic, which was actually not that bad from the viewpoint that you start something which is of this size, because it meant that we could actually a little bit slowly build it up. I would say that it took maybe a couple of years to build up it and get all partners on board and so on. Now we are about 200 research groups. So we are talking about maybe thousands of people, including all the students and so on. And we are like some 10, 11 partners, different industries, and many, many other stakeholders here who work together on this in a number of projects. There is maybe two aspects I want to highlight here. So one is, I think, for our environment here in Stockholm, it's a great opportunity coming together and having a platform where you can discuss this and you can, so to say, create new collaborations and contribute. But as this podcast now, right, we are talking about opportunities in a career and what happens. And for me personally, I think also to get this opportunity to be involved in building this and directing this has also been great, because the daily work, you teach and you work with your students and postdoc on papers and so on. Here, suddenly, someone says, okay, we get this opportunity to make a change. What should we do? How should we do it? How do you get 200 faculty members actually get on board and be willing? Of course, everyone wants the money, but how do you get them to realize that they won't get any money if they are not actually collaborating and contributing and participating, leading this initiative? So I think this has been very nice to also learn from that, but it's also going back a little bit to that roadmap. It also shows that if you are a few people who get together, it's actually not that hard, because people like to contribute and make something better out of our society. And that is the very same experience as with the roadmap happened here in Stockholm with Digital Futures. So now it's actually a very vibrant environment. We just had a conference we organize here. We have it every year. We call it Digitalize in Stockholm. 650 people coming from startups in Stockholm, undergrad students from the universities here, international peers coming, and big companies, small companies, and so on. And meeting and discussing what can we do and so on. And I really believe that it's nice to come together, and we all work in certain disciplines. We are in control, right? But sometimes it's nice to work and meet those people who are doing the interfaces to the technology. Or, we have legal scholars involved. What do a law professor think about the digitalization? What's the research going on there? What does a cognitive scientist, how are we, so to say, think about the part of the new technology from a psychological viewpoint? So we have this type of projects where we bridge this domain. Also social scientists. We have people doing technology history who are interested in this thing. So this is a little bit what we try to do at this Digital Futures. And so far, we just had our 5 years celebration. We are planning now for what will the next 5 years be, and how should we shape it, and what will be the new thing. And one big thing relates to what we are talking about here now is, how do you really go from doing experimental work at the university to doing experimental work in the city? How to get the citizens involved in doing research? How does that work? And I think it's really exciting to think how we can contribute to a better, in this case, a better Stockholm, but hopefully this can also lead to things outside Sweden and outside Europe for the future.
Well, first of all, I don't think there's a better publicity for this center than what you've just done. You got me excited just by listening to your words, even though I know about Digital Futures. Certainly, it seems to be also part of the zeitgeist somehow, that these big research centers are emerging, not only in Stockholm, but also we recently had on the podcast Munzer Dale from IDSS, also at MIT. Maybe we will have also another person involved with NCCR automation, directing, that we both know. As you mentioned, there's many initiatives that I find particularly interesting from Digital Futures itself in involving citizens. One of them being the KTH Living Lab. It's one of the things that piqued my curiosity the most, because it really, if I can summarize briefly for our audience, it's really buildings whereby people are actually living, of which you do measure data and on which you can actually perform experiments. And therefore, basically, you really are building the so-called smart cities of the future, but they physically exist today. There will be certainly a link in the description to Digital Futures, link in the description also to the events that have been connected to the center. I guess we're also slowly drifting towards the end of this episode. And at this point, I normally ask our guests for advice to future generations, particularly what to invest on in the future and what is very tough to solve, in your opinion. I'll let you maybe give some suggestions for those who are actually beginning in their career. Like, what would you have wanted somebody else telling you in this respect if you were to be starting today? Perhaps without spoiling the Bode lecture.
Sure. Thank you for that question. So I think we have touch upon a few of these things which I maybe would think as important for new generation. So maybe I just remind on a few things. You talked about time there at some point, right? So don't think that your studies, your PhD studies, for instance, it's some time that you are given. Use that time and dig into something deep, and dig into something deep that you like. Don't listen to too many people, or don't read too much about what you are supposed to do. Do what you like, and then try to find maybe an advisor or some collaborators that allow you to do that thing. I think for many people, when I look around, the ones that inspire me most are those who seem to be very excited about what they are doing. So this is one advice. Really try to, so to say, build up your confidence by investing into some interesting problems. And in doing that, I come back to another thing we talk about. Try to get that problem to both be linked to something which you can call it an application, or you can call it some motivation or so that you find in real life. So something that you can use either for just telling your mother what you are doing, or in general, it can motivate you a tough day or a tough week. You just know, okay, I try to contribute to that. But said that, think also at the same time on your problem as being a fundamental problem. So think about when you formulate your problem or work on that problem, that it's in many cases, it's not just applicable in one case. So think about other situation. How can you, so to say, maybe modify if you have a difficult problem? How can you modify the problem to make it simpler and so on? If it doesn't work any longer in that application that you were considered, think about another setting. So this thing, I think, maybe I did not realize that in the beginning of my career. I didn't realize that so much about research is formulating problem. It's not about solving problem. And I think this is good to know in the beginning, this, so to say, back and forth between formulating the problem, solving problem, see where the solution is useful. And the third and last thing would be the fantastic community and network that you have. So in the beginning, your network is often your study buddies, the friends that you have in the group or in some neighboring group, your advisor, and so on. Think about these people that you meet every day, but also the people that you maybe meet at conferences, at summer schools. Try to learn from them, listen to them, what they are doing, but also talk about what you are doing and what you get excited about. Because in the end, that is another thing I can reflect on if I go back. I didn't realize that some of the people I met a long time ago actually will be so essential for my whole career. Maybe not that I talk with them every day or so, but I sometimes think about something they said or something we were talking about, and I realize how smart advice these people came with or how fantastic ideas or so. So this learning from other people, not just learning from reading papers and reading books or listen to great talks on YouTube or so, but actually meet with people, ask them what they are working on, talk about what you are working on, and develop in that way. That's maybe my my spontaneous free advice to the next generation.
Well, I think it's great advice. So for all students out there, don't underestimate the interactions that you have, the serendipitous interactions that you have, say, at conferences or other events of the likes, particularly if you feel lost in the first few times. I think this is also a great point to close on a positive note, this wonderful conversation. Thank you so much, Karl, for joining us today.
Thank you. Thank you so much for having me. It was a great pleasure. Thanks, Alberto.
Thank you for listening. I hope you liked the show today. If you enjoyed the podcast, please consider giving us 5 stars on Apple Podcasts, follow us on Spotify, support on Patreon or PayPal, and connect with us on social media platforms. See you next time.